We continue with the Heisenberg-Lie algebra. We now seek to find the projection of the position basis onto the momentum basis, or I should say, from the mathematical point of view, the basis where the operator x is diagonal versus the basis where the operator p is diagonal. Now, how do we find the projection of one of these basis vectors on the other basis vector? We do that by sandwiching the operator p in between two of these operators. And there's a trick that we will use again and again and again in Lie groups and Lie algebras, that when we make this sandwich and put the p in here, we can let it act to one side where it takes the eigenvalue and let it act to the other side, and if we know what this operator is acting to the other side, that will form an equation which will allow us often to determine this particular projection. I'll go over that again. Often, when we have a projection of one type of space, the basis, onto another basis space, we can find what these projections are by taking an operator which has these states as eigenstates and acting forward to get the eigenvalues to form one side of an equation, and acting backward to get an operator to form the other side of the equation, thus getting an equation that can be solved for the projection. We do that explicitly here and let p act forward onto the k and give us the eigenvalue k, which comes outside, of course, times this projection. We then let the p act backward on the y, and we found last time in one of our previous discussions that p acting backward on a y is minus I h bar times d by dy. And that, of course, comes outside times this. Well, this forms a differential equation. In fact, we have reformed that by interchanging the two sides and writing by dy of this function right here. And remember, this is a function of two real variables, y and k. So we can say the derivative with respect to y of this function is equal to, and where I've multiplied by I over h bar, I times k over h bar times that function again. This has an exponential solution. E to the I over h bar k times y. This should be a wow right here. It's difficult to read. And I have set the normalization constant here to be 1 over the square root of 2 pi h bar. We have done that so that if one of these bases is normalized, the other will be normalized to within what we call a delta function normalization, something that we won't discuss later. But that's merely a normalization, and that's the way we choose the constant that's in the front. Now, this result is of the greatest importance. Namely, the projection is the directional cosines from the y basis, where x is diagonal, to the k basis, where p is diagonal, is this function right here. Therefore, this function gives us the directional cosines between the two bases. This means that the transformation from one of these bases to the other is the Fourier transform. Now, to understand the importance of this, we have to imagine that you have two different orthonormal bases, say in a three-dimensional space. One person, Bob, chooses x, y, and z pointed in one direction, and Tom chooses x, y, and z axes pointed in a totally different direction but having the same origin. How do we interchange the points, the vectors, the positions, the velocities, all of the information that Tom sees to what Bob sees? Well, we do that by knowing the relationship of each one of the vectors to each of the vectors in the other system. That is done by finding the angles between those vectors, or equivalently, the cosines of those angles, which are called the directional cosines. As you might guess, going from three vectors in one space, each projected onto three vectors in another space, give us exactly 9 different directional cosines. Those directional cosines give us the way to transform any piece of information relative to Bob into what Tom sees, or vice versa. And here we see something that is incredible. We see that the function with which we're so familiar, the Fourier transform, is in fact nothing but the directional cosine between the two equivalent bases in a Heisenberg-Lie algebra. What we will find as we move along is that the important functions that we're interested in theoretical physics, for the most part, can be written as directional cosines from one particular basis to another particular basis. Even going to a deeper level, we learn from a very early age that we can understand reality in terms of space and time. We look at objects in space as extended. We watch occurrences as they unfold in time. So this space-time manifold and the distribution that we see of it and the reality that we form of it is our image of reality. When we look at another basis, for example, momentum space, or where energy is diagonal, or where some other operator is diagonal, we cannot easily see or understand what those functions are, because they're not functions of the variables in which we formed the space, the variables in which we learned to form our space. So what we need to do is we need to take those energy functions and project them over so that we can see what those distributions are in our ordinary position space. Then we say, quote, oh, I understand this because I now see this probability distribution or this function written in terms of x, y, z, and t. And it's x, y, z, and t that we use for our ordering of reality. Therefore, the transformations back to x, y, z, and t basis, whether it's in quantum theory or in another physical theory, is critical. It's our visualization in terms of our space-time that leads us to feel that we understand something or have a methodology for ordering it. Another relationship that's incredibly important is called the completeness relationship. It's also sometimes called the decomposition of unity. The completeness relationship states that one, unity, can be written in the form of a projection onto K and a projection back into that direction. These vectors, here a bra vector and here a ket vector, written in the opposite form, mean whatever this acts upon over here projected onto K, whatever it acts upon here projected upon K in this direction. And integrate this over all of the different Ks. I should have a dk here to imply that integration. And likewise, an integral here over all of the dy's, so that I project onto each dy. When we say that one can be decomposed this way, we're really saying that these k's are complete for the expression of the space. If I project onto these and then put that amount in that direction, it's like projecting onto the unit vector in the x direction, which we get the coordinate x. So when we project something, like another vector, onto this k, we're really getting the coordinate in that k direction. And then we're multiplying that coordinate by a unit vector in that direction again. This integral then says we would basically have, or let's move over to the position where it's more obvious, if we had a three-dimensional space, it would say project a vector onto y, that would be like project it onto the unit vector unit I, and then that would give us a coordinate x, which would be in the x direction, another one in the y direction, and another in the z direction. So that would give us the equivalence of saying project a vector r onto the vectors I, j, and k, and then write it as r vector is equal to x times I plus y times j plus z times k. Thus a vector psi, to write this out, can be written relative to the position space in the following way. We can write psi projected up onto y, which of course gives us the components of psi in the y direction. And we can insert in here a unit vector 1. That's a complete decomposition in terms of k. And when we do that, we end up with the following equation, where we have an integral over k of y onto k, and we know what this is already from our previous work. It's 1 over the square root of 2 pi h bar, integral over dk, again this is an integral over dk here, of e to the I over h bar ky, k times y, and this means right here that we can write psi on the y basis as 1 over the square root of 2 pi h bar integral over dk of e over I over h bar k times y psi of k, which is the Fourier transform. That is why in the previous lecture we said the projection of y onto k as this exponential gives us the Fourier transform as a relationship between a vector's components in one basis to a vector's components in another basis. This explicitly shows the deep basis and meaning of the Fourier transform with its origin in the nilpotent Heisenberg-Lie algebra. To give an example that I was imagining a while ago, we need to reflect on this concept in infinite dimensions and compare it to a three-dimensional space. We could imagine here our y space and our k space having vectors that point in some different direction. And the projections of each one of these y's onto each one of these k's is precisely this constant times e to the I over h bar, that value of k times that value of y. We can compare that to the three-dimensional case with which you're already familiar. That covers our concepts of position and momentum, the two bases that we normally think of when we think of this algebra that consists of x and p and capital I, which always has the eigenvalue h bar. But we can now look at another possible basis for the space that has to do with the evolution of a particle. When we talk about the evolution or the time evolution of a particle, we're really talking about dynamics. So now we want to look at the dynamics of a particle as it moves along in time. We postulate that a system evolves in time by the transformation u from t naught to t. This operator will take us from t naught to the time t, and that this operator is e to the minus I over h bar h times t minus t naught. Immediately it's easy to verify that if we act with the differential operator I h bar d by dt times u times psi, then we get h times u times psi. Thus we can also write this as the differential equation I h bar d by dt of psi of t, and what we have done is we have written this together as a combination as saying this is now psi of t relative to t naught, which we are going to say take equal to 0, is equal to h times that same vector. So a vector evolves in time in a way so that it satisfies this differential equation. H is yet unspecified. Or we can say that it evolves in time according to this unitary operation here. So on the one hand, we have the time generator of time translation. So this becomes a new type of operator that moves the system forward in time, and it's equivalent to this differential equation. Now, from our knowledge of physics, we know that this H, as we call it, this time development generator, is normally taken as the Hamiltonian, which for a free particle is p squared over 2m, and for a particle that suffers a potential interaction is plus the potential v of x. This gives us the total energy for a simple system where the potential exists and where we have no dissipative forces. So, writing this as a simple equation now, we can write this in the position basis by saying, let's take y, h, psi of t. And h, of course, is going to be p squared over 2m plus v, again times psi of t, which is the differential operator IH bar d by dt times psi of t. And by the following manipulations, we can convert that into a differential equation that will give us the time evolution of the system. Specifically, we can take the 2m and let it pass outside of the y vector. P becomes minus IH bar d by dy, and therefore we square it because the p is squared, moved out of the system. And v of x, of course, just becomes v of y, because x, any function of x onto the eigenvalue y, gives us the eigenvalue y, so some function of x operator will give us that function of y. So we have now collected this entire expression out to the left of y, multiplied by y psi of t. This is the vector as it evolves in time as expressed in terms of the position basis. On the right-hand side, we're able to bring out IH bar, and d by dt passes right through the y because y does not have any explicit time dependence. This again gives us a psi of y, and so now when we write this in the form psi of y and t, because psi now depends on the parameters y, which we're now looking at as one-dimensional, we have minus I times a minus I, which gives us a minus sign, h bar squared over 2m, d second by dy squared plus v of y as a linear operator acting upon psi of y and t, and that has to equal to IH bar d by dt of the same function. This equation is extremely important. It forms the foundation of our non-relativistic quantum theory, and it's called Schrödinger's equation. In 3 dimensions, it's easy to show that that same derivative, which is going to be p vector squared over 2m, now becomes transformed into a del operator with respect to y. That is, a second partial with respect to x, second partial with respect to y, plus a second partial with respect to z. For the relativistic case, we get something very similar. In that case, we must use the relativistic Hamiltonian. And that was for a reason for the importance of going through the theory of relativity before we got to here, so we could easily generalize this to that situation. So, all in all, we have had to make a new assumption. We have had to say, we will now allow vectors to depend upon a new parameter. This is actually an action that evolves the vector through this unitary transformation, and this is unitary if this operator is Hermitian, as it will be. This unitary operator will evolve us from one time t naught to a new time t. This is just like a translation or rotation or any of the other one-parameter group operations that we'll be studying as we go along. This would be comparable to a group operation, whereas the h is going to live in the Lie algebra itself. And we can see that h indeed does live in this Lie algebra. It is some function of p and some function of x. So it could be represented here as some presumably analytic function of x in a Taylor series expansion. And the p squared is, of course, the square of one of the operators. This then gives us the time evolution, and that time evolution can be rewritten in the form of a differential equation. Casting that in the position representation, we see how we can get, using the decomposition of the projection in the y direction, how we can get, in fact, Schrödinger's equation. So now we see the Heisenberg algebra from a new point of view. This one-dimensional problem we could see in the energy basis. By the energy basis, we mean the basis in which h is diagonal, not x and not p, but some combination of the two, p squared plus v of x, where v is the potential. So in addition to a basis for the XPI algebra, where we have x or p diagonal, one can now seek a whole new basis, which is extremely important. Namely, we can seek a basis in which h is diagonal. And we can imagine that h times some eigenvalue e, a vector labeled by the eigenvector E, is E times that state back again. So namely, H is diagonal. Now if the particle is free, H is p squared over 2m, and this becomes the same as the k basis that we had before, so we don't have anything new. But if V is a central force, then this becomes a rather complicated problem. H is now p squared over 2m plus V of r, if this is a central force, and can be diagonalized as some eigenvalue E. But the E spectrum is not a complete basis, and in 3 dimensions one can diagonalize other operators, as you know from quantum theory, namely L squared and Lz, the angular momentum and its z component, to get the energy, the angular momentum, and its z component. We will see later that an orbital angular momentum tensor, Lij, is such that it gives us a LieAlgebra.03, which is the same as SU2. And that algebra also lives halfway between the y and the k basis. That happens because Lz, the angular momentum in the z direction, is x times py minus y times px. So this is this basis here of the L and the m, the angular momentum and its z component, is a new basis that will live when we get to 3 dimensions exactly halfway in between the position basis and the momentum basis in a symmetric manner. One way that we can see this very clearly is by going to a harmonic oscillator algebra, where we have our energy, or a Hamiltonian, I should write here, as p squared over 2m plus k times x squared over 2. This is, of course, the kinetic energy of the particle, the one-dimensional oscillator, and this is the potential energy, 1/2 kx squared for the oscillator, and that can be rewritten in a way that is totally symmetric between the x and the p. So if we were to choose that as the Hamiltonian, we would in fact end up with a system that was exactly symmetrical in terms of the energy eigenvalues between an x representation and a p representation. We can see then that if we were to look at a 3-dimensional harmonic oscillator, we would end up with an orbital angular momentum and its third component, which were totally symmetrical between the spaces, and also an energy that's totally symmetric between x and p. So this would be a new basis that would exactly live halfway between the position and the momentum basis. Naturally, therefore, we can project it onto either of those two bases. It will be more interesting, however, to actually generate a new type of Lie algebra associated with the harmonic oscillator and study that.